Today we will have two speakers, as Xiaofeng mentioned. The first one will be Nora Weickgenannt from the University of Frankfurt. She's she she's a student at the PhD student at the University of Frankfurt, and she will get his PhD very soon, as far as I understand. And she has done very relevant work for the subject of spin hydrodynamics and polarization. And the second speaker will be Yi Yin who is a scientist, presently a scientist at the Institute of Modern Physics, the Chinese Academy of Science. He was he got his PhD at the University of Illinois in Chicago with Mikhail Stefanov as a supervisor. Then he had two postdoctoral positions at BNL and MIT with Krishna Rajagopal. So the topic of today, as Xiaofeng mentioned, is spin polarization in relativistic heavy ion collisions, and specifically, as far as I could see from the titles and the slides, about the dissipative corrections to the spin polarization, which is becoming a very interesting topic, and with a special emphasis for, as far as Yi Yin is concerned, on the spin alignment, who is one of the yet, say, very unclear problems in the very unclear observations in the heavy ion physics. So I'm very pleased to chair this session because these are relevant topics, and the speakers have done excellent work in this respect, and I'm happy to give the first word to Nora Weickgenannt. So you have 30 minutes. Then, last remark, there will be time for one or two short questions at the end of each talk, and then a discussion session of half an hour, about half an hour will follow. So for more important comments and questions, please wait till the end of the two talks. So Nora, please.
Yeah, thank you. So as mentioned, I want to talk about how to get from quantum kinetic theory to spin hydrodynamics. Oh, so now I cannot move anymore. It just worked. Sorry, I stopped sharing my okay.
Yeah.
Okay, so so let's start with some short motivation. So in non-heavy ion collisions, there's some large orbital angular momentum, which can be converted into spin, which means that the global rotation can lead to polarization. And this was measured, and actually it was estimated the vorticity from the Müller approach to global equilibrium. And this was so high that in this famous Nature paper where the collaboration, the core glue and plasma was called the most vertical fluid ever observed. So how's this spin polarization measured? In the weak decay of a lambda hyperon, and the daughter particles are emitted preferably along the polarization direction. So from the angular distribution of the momentum in the hyperon rest frame, one can immediately conclude to the polarization. And this was done, and actually the global polarization, so the polarization along in the global, so the momentum integrated polarization along the angular momentum direction was in very good agreement with the experimental data and the phenomenal calculation, which assume local equilibrium. However, the local polarization long time showed the opposite angular dependence for the momentum. And recently there were more developments was resolving this puzzle. Still, the question about dissipative corrections to the polarization is still open. So the question is, can we derive this about the spin hydrodynamics? And I want to show how to get from quantum field theory to hydrodynamics. So we start with quantum field theory, describe the spinors and Dirac equation. And the next step is to obtain the Wigner function by the Wigner transformation, and also the equations of motion for the Wigner function. So the Wigner function is defined as the Wigner transformation of the two-point function. And we start from Dirac equation with a general interaction term rho, and derive the equation of motion for the Wigner function, which then looks like this. So there's a collision term on the right-hand side here. And the idea is to calculate this collision term up to first order in H bar. So the next step going from the Wigner function is to go to distribution function by putting the spin to the phase space and obtain some Boltzmann equation. So we define a distribution function in a large phase space by the vector part of the Wigner function, and the actual vector part of the Wigner function is contracted with this spin variable as mu. And then from the equation of motion for the Wigner function, we derive some Boltzmann equation for the distribution function, which has some collision term on the right-hand side. And then we calculated the collision term from quantum field theory using the Wigner function formalism and took into account non-local particle scatterings. So one finding is that the off-shell terms cancel, and in the end one has an equation of motion for the on-shell distribution function, which looks like this. And we have a non-local collision term, which means that the particle positions are displaced by this delta mu's, which are of order of the quantum wavelength H bar M. So the interpretation is that the particles scatter with a finite impact parameter. So there's some orbital angular momentum in the collision, which can be converted into spin. Then from the condition that the collision term has to vanish, we find the local equilibrium conditions. And the solution with the non-local collision term is this one, so just this usual Boltzmann distribution function. And then we have some contribution from the vorticity and this dipole moment tensor. And if we impose that the collision term should vanish, we actually also derive the Killing condition, which means that actually we're in global equilibrium. So also the left-hand side of the Boltzmann equation is fulfilled. And then one can insert this and calculate the equilibrium polarization, which is then along the double vorticity. So this means that the fluid is polarized along double vorticity through the non-local collision term. So let's come from kinetic theory to hydrodynamics. So relative dynamics is usually based on the conservation equations for energy, momentum, and charge. And the idea in spin hydrodynamics is to promote the spin tensor to an additional dynamical quantity. And its equation of motion is derived from the conservation of the total angular momentum tensor, which is the sum of some orbital part and the spin tensor. And its conservation implies that the divergence of the spin tensor is given by the antisymmetric part of the distribution of the momentum tensor. Okay, so the last step is to calculate the currents from the distribution function, which are moments of the distribution function, and follow hydrodynamic equations of motion. And one can express the charge current and moment tensor and the spin tensor by integrals of the distribution function from the macroscopic definitions. And if we apply this theorem to the Dirac log equation, one obtains the so-called canonical currents. And this is the canonical momentum tensor. And remember that the antisymmetric part of this momentum tensor is responsible for the conversion between orbital angular momentum and spin. So looking at antisymmetric parts, there's some part which comes from this dB mu, which is some interaction contribution. And then there's also this part which comes from the sigma s mu lambda partial lambda term. And this is even there for free fields, and it's also there for in global equilibrium. This means that the spin tensor, in the canonical form, is not conserved for free fields or global equilibrium, and is not really consistent with the physical picture, because we expect that the spin density changes through collisions and only until the global equilibrium is reached. So here one should note that the microscopic definitions of the occurrence are not unique. So we have some pseudo-gauge freedom, so we can redefine the momentum tensor and spin tensor with these transformations. And this leaves invariant integrates of motion and also the global charges, which are the hypersurface integrated quantities. And the idea now is to find some pseudo-gauge with a clearer physical interpretation. And this is, for instance, this HW pseudo-gauge. And this were derived for free fields in the original work, and we generalized this to the interacting case. And then the intermomentum tensor and the spin tensor look like this. So the intermomentum tensor probably has some familiar form, and the intermomentum tensor consists of this. The spin tensor consists of this type of moment and then some derivative term. And from the Boltzmann equation, one can derive equations of motion. The divergence of the intermomentum tensor is then related to the p mu being a collision invariant, and this is a collision invariant, this vanishes. On the other hand, the divergence of the spin tensor is proportional to the sigma s mu nu and the collision term. And since this is not a collision invariant for non-local collisions, in this case, this is much part of the intermomentum tensor. On the other hand, for local collisions, this is a collision invariant. So then the right-hand side of this equation is 0. So the local collision term has been conserved. On the other hand, for the non-local collision term, there's some conversion between orbit angular momentum and spin until global equilibrium was reached. And this leads to spin alignment with vorticity. There's also the possibility to include electromagnetic field in this formalism to derive spin magnetohydrodynamics. And the idea here is to perform an HW pseudo-gauge transformation for the fermion parts and some well-funded pseudo-gauge transformation for the electromagnetic parts. So one obtains some gauge invariant splitting of the total angular momentum with a non-zero spin tensor here. And there's some coupling in the intermomentum tensor between the electromagnetic fields and the dipole moment. One can then also derive equations of motion for the spin tensor. So the divergence of the spin tensor is then non-zero because there are external fields. And actually this term is similar to the classical spin precession. Okay, so let's come back to our picture. We already have the hydrodynamic equations of motion which follow from the conservation laws. However, in the derivative case, these conservation laws do not provide a closed system of equations. So we derived spin-magnetic theory from quantum field theory. Now we want to derive additional equations of motion which are needed to close the system of equations from the kinetic theory. And for this, we use the method of moments, and we generalize it to include spin degrees of freedom. So the first step is to decompose the currents with respect to the fluid velocity. So this is just the most general decomposition one can have with decomposing with respect to some vector. And we see that we have 4 plus 10, which is the symmetric part of intermomentum tensor, plus 24 degrees of freedom. This is because this is lambda mu used antisymmetric in mu and nu. However, we have only 1 plus 4 plus 6 equations of motion. So as mentioned, we need additional equations of motion to close the system of equations. And for this, we know that all components of this occurrence can be related to moments of distribution function. Like for this, what we call n tilde mu and spin energy tensor is related to this moment of the distribution function. This angular brackets just mean that it's integrate of a momentum with the weight of the distribution function. And now we derive additional equations of motion from kinetic theory. So, as already mentioned, the non-local collision term vanishes only in global equilibrium. So, usually the moment expansion one starts from the local equilibrium state. So the first question is how to define local equilibrium as the starting point of dynamic expansion. And actually, the issue that we're having with this local equilibrium is that the non-locality scale of the collision term is smaller than the scale on which this equation happens. And the solution is to treat the vorticity on a different scale than the other gradients. So we impose this ordering of scales, so the delta, which is next to the non-locality, has to be smaller than the mean-free path. This is necessary for molecular chaos. And the mean-free path has to be much smaller than the hydrodynamic scale, which is the inverse gradient of the hydrodynamic quantities. This is necessary for the hydrodynamic expansion. On the other hand, we impose that the delta is much smaller than this LV, and this LV is the vorticity scale. And then we say that the vorticity scale is smaller than the hydrodynamic scale. And this allows for a definition of local equilibrium. And we choose this ordering in a way that the expanded in the spin degrees of freedom, which is delta over LV, is of the same order as the hydrodynamic expansion, which is the mean-free path of the hydrodynamic scale. This means that in local equilibrium, we can neglect contributions which are of order delta over hydro. And this means that the non-local collision term vanishes if the spin potential is equal to thermal vorticity. Okay, now having this power counting, we can expand the distribution function up to first order in H bar and gradients. So we have this term which comes from the equilibrium distribution function. And then we parameterize this deviations from equilibrium like this. And here what multiplies the maximum now is the spin potential. It is the sum of the thermal vorticity, which is the equilibrium part, and then it has some dissipative corrections. And then one can define dissipative total moments, which are these rows, which are also present in the spinless theory. The new additional degrees of freedom are these taus, which come with the spin variable here. And then the delta F can be expressed in the basis of the dissipative moments. Okay, we also choose some matching conditions, which are Lambda frame, so these are the matching conditions. And in the presence of spin, we need some additional matching conditions to define the spin potential. And we choose that U lambda, J lambda mu is equal to this equilibrium value. So this defines spin potential in local equilibrium. And then from the conservation laws for N mu, T mu, and J lambda mu, one can derive equations of motion for the thermodynamic potentials. And furthermore, from the Boltzmann equation, one can derive exact equations of motion for the spin moments. And I just put one here. So there are lots of terms. And so on the left-hand side, there's some collision term. Now, what is important to note here is that they couple, so all of these R's couple to moments of different R's and also of different tensor rank. So we have some infinite tower of coupled equations. So we need some truncation procedure. And the idea of following this result is to approximate the moments which do not appear in the conservation laws, but laws which do appear. In conventional hydrodynamics, these are the particle diffusion, the heat flux, the bulk viscous pressure, and the shear stress. So these are 14 degrees of freedom. This is usually referred to as the 14 moment approximation. Now in spin hydrodynamics, we have additional numerical moments which come from the spin tensor. And these are the spin energy, the spin pressure, the spin diffusion, and the spin stress. There are 24 degrees of freedom. So we call this the 14 plus 24 moment approximation. And now at this point, which moments are promoted to be dynamical depends on the form of the spin tensor, because these are the ones that are treated dynamically. So at this point, the H dependence enters. Okay. Then we have to deal with the collision terms, which have in general this form. So there's one part which depends on the dissipative spin moment. Then there's some part which has a difference of between the spin potential and thermal vorticity. And then there's some part which comes from non-local collision term and depends on the thermal shear. And now all we have to still do is to invert this matrix, this V, to obtain the final form of the equations of motion. And then this equations of motion look like this. So in the front there's some relaxation time, which is obtained from the local collision term. And on the right-hand side, there are again lots of terms which all have different transport coefficients. And what is shown in violet here are those which remain the Stokes limit, and the first one of them comes from non-local collision term. And there are similar equations also for the other dynamical spin moments. So in the end, we have some closed set of relaxation equations. And then we can also calculate the relaxation time for the spin moments independent of mass over temperature. And we find that the spin relaxation times of the same order as those of the other dissipative moments, which are dashed lines here. They're just slightly smaller here. And this actually means that it makes sense to treat the spin moments as dynamical, since if they were orders of magnitude smaller, then we would not need to take into account dynamics because they would relax so fast that you could not see anything. But instead of the same order, it actually makes sense to treat them also dynamically. Okay, finally, we can connect to the observable Lanzhou correlations, which is a so-called Pauli-Weinski vector. In equilibrium, it has this form, which depends only on the spin potential, which equilibrium then is also equal to thermal vorticity. And now one can express the dissipative corrections through the dynamical spin moments, which looks like this, and they have different powers and momentum, and depend on all the dynamical spin moments. So to get an explicit expression, one actually has to solve the phase of motion and obtain these spin moments. However, one can already say something in the Navier-Stokes limit. So far, we kept the terms of the second order in the case of motion, which corresponds to transient hydrodynamics. If one keeps only first order terms, one obtains the so-called Navier-Stokes limit. And in this case, there are no additional dynamic quantities. So everything can be expressed in terms of these fields and the derivatives. Then one can obtain some expression for the Pauli-Weinski vector, which is rather lengthy, and I don't show it here. I just want to show one contribution which comes from non-local collision term, and is actually independent of the spin potential. And in fact, it gives some contribution from the shear tensor to the local polarization, so to the one that depends on momentum. And after the momentum integration, it vanishes. And this is actually similar to a term which was obtained in other approaches and turned out to be important for the description of local lambda polarization. So to summarize some findings from this, so the collision term has local and non-local contributions, and the local contributions lead to the spin relaxation times, which have the same order as the relaxation times. The non-local parts of the collision terms contribute to the Navier-Stokes limit. And furthermore, to say something about this pseudo-gauge dependence. So in principle, the microscopic theory, which is the full theory, should be independent of the pseudo-gauge. However, what we do is we impose some separation of scales and some truncation procedure. And at this point, we make some pseudo-gauge choice. And what with all of these microscopic quantities, we choose that which we treat dynamically. And this that depends on the pseudo-gauge. So the hydrodynamics in different pseudo-gauges can be different. Okay, and on the last few slides, I want to say something actually about spin alignment and tensor polarization. So spin 1 particles feature additional degrees of freedom which are related to tensor polarization. In heavy ion collisions, this leads to the so-called spin alignment. And this was measured, but from proofs, and it turned out that this is rather large, and there's not really any explanation why this is so. And so the question is whether maybe this can be explained from the dynamic approach, so maybe we can derive the hydrodynamics for spin 1 particles. So the difference between going from spinless hydrodynamics to spin 1/2 hydrodynamics is that we have an additional equation of motion, which is related to conservation of the total angular momentum, So we treat the spin tensor as an additional dynamic quantity. So going from spin 1/2 to spin 1, we have tensor polarization as an additional degree of freedom, but this is not related to any conserved current. So in principle, there's no need to introduce any additional dynamic degrees of freedom. So can our formalism be used to describe all the tensor polarization? And the answer, of course, is yes. We just have to work a bit more and repeat actually all the steps that we did for Dirac fields, for Brucker fields. So we start from Rieger function for Brucker fields. Again, we define the distribution function in a large phase space. And what is new here is the last term, which is quadratic in the spin variable. And this corresponds to the tensor polarization part. Then from the Brucker equation, one can derive some equation of motion for the on-shell distribution function f, which is formally the same, although this coordinate term of course looks different. And then one can do hydrodynamics with tensor polarization. And actually one finds that in local equilibrium, the tensor polarization vanishes. On the other hand, in the distributive case, there's some tensor polarization, and this is described by the moments which are quadratic in the spin variable. And then from the Boltzmann equation, one can derive equations of motion for the tensor polarization moments, which are coupled to the usual moments through the collision term. So as already mentioned, the tensor polarization moments are not related to any conservation laws. So it's actually expected that they relax on shorter time scales than the usual dynamic variables like the commands of the intermomentum tensor. This means it's reasonable to approximate them by the Nora-Stokes values. And this one can calculate for different psi's. So for instance, this psi1 we knew here, which is proportional to the shear stress tensor with the Nora-Stokes limit. And then the spin density matrix, which is measured in heavy collisions, can be expressed in terms of these psi's. So it has different coefficients in front of it, which one can calculate. And then one can insert the solutions for the psi's into the spin density matrix. And we see that there come some contributions from the shear stress tensor to the spin density matrix, so also to the tensor polarization. And this is some first order effect, and it's expected to be rather large. And furthermore, after the full system reaches Navier-Stokes limit, there will be proportional to the shear tensor. And actually, I find it interesting that there was a similar result actually from another group, and we will hear about this in the next talk. So, to summarize, we derived the second order spin hydrodynamics from quantum field theory. And for spin 1/2, we obtained the distributive corrections with the Pauli-Banske vector, which depend on all dynamical spin moments. And in the Navier-Stokes limit, they have some contribution from spin potential and shear. So this we have some new theory with new dynamical quantities. We still need a new numerical implementation of this equation of motion to compare to experiment. And for this, next thing to do is some causality and stability analysis of the second order equations of motion. On the other hand, for spin 1, we derived dissipative correction to the tensor polarization, which can be described by the Navier-Stokes limits. And these depend on the usual moments, like the shear stress tensor. And that gives some first order contribution to spin alignment. So here one actually can use the conventional hydrodynamics, and the numerical implementation is in progress. And another new direction is actually to include electromagnetic fields and spin method of moments to derive the dissipative spin magnetic hydrodynamics. Thank you.
Thank you very much for this very nice and comprehensive talk. As I said at the beginning, there is a time for one or at most two short questions, and the more detailed discussion will follow after the end of Yin's talk. So are there any urgent questions?
Yeah, Nora, I have a question about the
Yeah. So can you please raise hand so that I can?
Oh, yeah. Raise hand.
Introduce the
Where
question.
to raise hand?
Okay, so question by Chung Wang. Yeah, please.
Yes. Yeah, you said that there's a first order contribution to spin alignment. So is this conclusion from the hydro derivation or other theory? Can you show what it looks like?
Well, yes, it is this. So this Rossi-Zurich is what is special an experiment, and it depends on this moment. I just put one here, but yeah, but also the other one can be expressed in terms of
So why you say that this is the first order in what? In the gradient?
In gradients.
In the gradient, I see. So this is a hydro, is a conclusion from hydro, spin hydro.
Yes.
Okay. Okay, so thank you.
So I don't see any more raised hands. So I would like to thank Nora again and go to the next talk by Yin Yi, whose title is Demystifying Spin Alignment Puzzle in Heavy Ion Collisions. So same time. So please, you can start. I cannot hear you.
Sorry, I should mute myself. So can you hear me now, Francesca?
Yeah, we can hear you.
Okay, great. So yes, and so today we will focus on is the spin alignment. The fermions has already been nicely reviewed by the Nora. So it is commonly believed that the current observation and the spin alignment cannot be interpreted in the conventional mechanisms. But today I wish to convince you that this might not be the case. If we consider the spin alignment in the near brain, we would see several important contributions which has been overlooked. And interesting consequences of my of this study is actually spin alignment is a sensitive and a new probe of the immediate property of the vector mesons. So let me begin with the context. So we wish to understand the QCD phase structures and the beautiful measurement and the polarization of fermions and the spin alignment of the vector mesons. In fact, the probes the QCD phase structures. So let us just imagine that we change the temperatures. We have the hydrogen gas, and then we have the quark-gluon plasmas. Because the pions does not carry the spin, but the gluons and the fermions and the quarks carry spin. So we see the significant changes in those in the spin carriers around the TCs. So in principle, the spin measurement should be very sensitive to the QCD phase transition. But to make the story even more interesting is if you think about those spin carriers, in particular the vector mesons, their immediate properties will change, in particular change dramatically around the TCs, so that if we could infer the immediate properties of the spin carriers, we could also learn much about the QCD phase transitions. So in this talk, my focus will be on the spin alignment. So let me begin
yes. Can you get rid of that bar at the bottom of your slide?
Like
okay,
this?
Thank you. Yes.
Okay, sorry for that. All right. So okay, and so let me just remind you that why the vector mesons are very useful. If you think about the heavy flavors such as the J plus size, we always use it as an indicator of the QGP formations. if we tend to the light flavors, we also know the changes dramatically. So by studying light flavors, when we know about the QCD phase transitions, and clearly there's much progress both from the experiment side and the theory side in the study of the Weickgenannt invariant properties, but it's still fine to say that their properties are still not fully constrained from the theoretical side and from the empirical side. For example, we don't know how to compute the spectral function from the lattice at the finite at very high barrier densities. And also just by looking at the dialectical data, we are not fully understand the property of phi or omega mesons. So the central thing of my talk here is I want to ask, can we obtain the new insight into those the immediate property of Weickgenannt mesons just by looking at the spin alignment? So this is just, so this slide reminds you about the basics of the spin alignment. So put in a nutshell, the spin alignment is a measure of the imbalance between the different spin states. So the S here just S0 means that the spin aligns in the direction perpendicular to the quantization axis, and S equals to 1 and S equals to -1 just means that the spin are aligned in a plane which is parallel to the quantization axis in head. So you can define the spin alignment, which is the deviation of the 0,0 components of the spin density matrices from the 1/3. A useful way to write down this expression is showing in the middle. So basically, this tells you that there's an imbalance between the spin states living in the plane transverse to the head and the perpendicular transverse perpendicular to the head and parallel to the head. So if everything is isotropic, clearly we expect that there's no preference in the occupation of the spin states, but therefore the non-zero spin alignment implies is some anisotropy. So here I wish to emphasize that for these 3x3 matrices, the spin alignment is a component of the symmetric part of the matrices, meaning it transfers as a rank 2 tensor in the spin space. So this is qualitatively different from the polarization, which corresponding to the anti-symmetric part of this 3x3 matrices, and this spin polarization is the pseudo vectors, not the rank 2 tensors. Because of such qualitative differences, we should always keep in mind that the mechanism which generates the spin polarization might not be the main mechanism which generates the spin alignment. So here comes the data. I show you the data on the kaons and also from the phi. And I didn't put a plot, which I should. We also know there's data from Alice about the JEP side, the heavy flavors. So if you look at the magnitude, it's order of 1% and it can be even larger than that. What is interesting is if you talk about the psi, the deviation of this rho 0,0 from the 1/3 baselines, and its psi can depend on the species. It depends on whether you are talking about the phi or talking about the kaon. And if you look at the PT dependence or the centrality dependence, you also see it looks quite non-trivial, and it also even changes the psi if you change the centrality, as shown in this very red figures. So now comes to the questions, how should we interpret these results? One of the popular model which tries to interpret result is based on the recombination pictures. You assume the polarization of the Weickgenannt mesons coming from the polarization of the constitutive quarkers. So each quark carry is proportional to vorticity. So you found that this spin alignment is proportional to the vorticity squares. And immediately we have received several issues here. The first of all is this vorticity square is the second order ingredient expansions. What does that mean? It assumes that there's no contribution at the 0th order ingredient, no contribution at the 1st order ingredient. Everything begins with second order. And therefore, we should be not surprised that the model predictions using these second order contributions is a surprise. It's at least the order of magnitude smaller than what we see in the data. And another thing I want to emphasize is the prefactor to a good approximation is 1/9. And the psi is fixed. It has no explicit dependence on PT, explicit dependence on rapidities, and also does not even depend on the species of the mesons, as well as their in-medium properties such as the thermal mass and the width. So this clearly is not we see even at the qualitative level in the data. So fortunately, such interpretation is based on the recombination models. And what I wish to show you next is if we assume the vector meson is near equilibrium, we see the qualitatively different expectations. So here we go. So we need to set up the formalism, we should use the Weickgenannt functions. So this is the Weickgenannt function with respect to u mu, the operator which creates a generic charge neutral vector meson. So it's a tensor carries the Lorentz index. And you can show is if we are interested in the symmetric part of this Weickgenannt functions, you can connect it to the symmetric part of the density matrices if you project it with the appropriate polarization vector pairs. So to make it further progress, we can further we can further decompose this symmetric part of Weickgenannt functions in terms of the spin averaged distribution in order by FVM here plus the terms, the remaining terms, the T mu mu curly T mu mu. So this is the traceless tensors reflecting the differences due to the spins. So with the relation between the Weickgenannt function and the density matrices, we could directly compute the spin alignment from the components of Weickgenannt functions. So this is very nice because the Weickgenannt function can be determined using the theoretical method. So now let me begin by showing you the results at the zeroth order. Essentially, we consider homogeneous systems. Everything is fully in equilibriums, and we ask whether we get a non-zero spin alignment. Of course, you can directly derive the results in these slides using the known property about the immediate, about the vector meson propagators immediance. But here I want to show you a very intuitive way to understand it. So let us just consider the vector mesons, which is moving in particular directions, and its angle to the quantization axis n hat is denoted by theta n's. For fixed velocities, there are 3 helicity states, so we need to add the contribution from each of them. If you consider the helicity 0 state or the longitudinal state, you found the contribution is given by its distribution multiplied by cosine theta squares, the projection of the velocity to the quantization axis. You can do the similar you need to do the similar things for the helicity 1 moles, and then you subtract the average run. Of course, if the longitudinal distribution is the same as the transverse longitudinal, you wouldn't get any spin alignment. And that's why you get these prefactors, the differences in the occupation of the longitudinal helicity 0 and helicity 1 moles. But we should remind ourselves that it's well known that the energy degeneracy between the transverse and the longitudinal helicity is simply splitted because of the median effect, because there's no Lorentz symmetry and they don't have to be the same for those 2 different helicity modes. And it's just because you can occupy the more longitudinal modes as compared with the transverse modes, or the other way around, you would get a non-zero delta spin alignment as shown in the last equation here. So it's proportional to the energy differences with the prefactor, which is determined by the relative velocity projected along the quantization axis squares. And if it's different from 1/3, you get a non-zero results. So that's it. Of course, you can see that if you do the integration of momentum over the space, if you consider longitudinal expanding systems that like the fireball created in heavy collisions, you will get the non-zero results. If also you can select the particles with large PTs, you also get the non-zero results. So this is just examples of the energy splittings. So this is the textbook results. The transverse photon is different from the longitudinal photons. And what is more interesting is this is the discussion of the phi dispersion at the very high nuclear densities. And you see that the splitting grows if you are increasing the momentum, and at the 2 GeV momentums, the splitting can be as large as the 50 MeVs. So now we can ask the questions. Is there any phenomenological implications? So for let us illustrate this effect by considering the quantization axis as the y-axis. So as I just said, it should be proportional to the velocity in the y direction squared, and see whether it's different from the 1/3. There are two sources that it can be different from 1/3. The first source is the relative velocity between in the xy plane is different from the relative velocity in the z directions, and another source is the difference between the x velocity and y velocities, and later can be easily estimated using the V2 flow, the standard spherical harmonics. And in these figures, I'm showing you these are parallel, these differences in the flow in the XY plane and the VZ plane, just assuming the built-in backgrounds. So we see that at very low PTs, it's negative, and then it turns to the positives. And this can be easily just understood. At the low PTs, the most of the particles are moving in the Z directions, but the PT is very large, and the particles are moving in the XY place. So what the main essence I think I learned here is just considering this energy splitting effect, you will see a non-trivial dependence on the kinematic region in the phase space. So in a very easy way, in a very simple and intuitive ways, you can plug in your favorite values here, and the conclusion is, if this energy degenerate splitting factor is out of like 20 or 30 MeVs, you will get a 10 to the -2 signatures, which is already comparable to what you see in the data. And you can do the similar things by choosing a different quantization axis. So this is the quick summary. We already see something very interesting. By measuring the vector mesons, we may get access to the energy splitting, the prominent median effect, which is, as we believe, is very difficult to measure otherwise. But interestingly, the information encoded in the spin alignment is even richer. So to see this point, I need to go to the next order ingredient. So I'm working on the first order ingredients. Let me first remind you what we should do for the spin average distributions. So basically our strategy is we should write down all these possible terms that is allowed by the symmetry and the first order ingredient. So for this spin average distribution functions, we have the expansion term proportional to theta here, and there are many other terms. This is the standard procedures where when we are doing the freestyles, we need to take into account the slight deviation from equilibrium, which are expressible in terms of the bulk pressure or the shear pressures. And what is maybe less known is you can just do the similar procedure for the spin dependent part, which is denoted by this curly tau mu here. So there are several contributions from the temperature gradient, from the expansion rate, but what is most important one is the contribution, which is proportional to the shear, denoted by sigma alpha beta here. Depending which helicity state you wish to project it to, there are three independent contributions, which is allowed by the symmetries. Under certain conditions, we can simplify this expression, say if you ignore the differences between the different helicities states in equilibrium, then the B1, B2, B3 equals to each other, and you get a very compact form expression at the end of these slides. So this is important. So it's a proportional to the shear, and the proportionality is we denote this proportionality as a new transport parameter, namely the shear polarizability. It tells us to what extent that the tensor polarization can be developed in the presence of the shears. So this is very important. So here comes some physical interpretations. The simplest way to interpret our results is go to the particle rest frames. So in these cases, the tensor part of the Wiggler function is simply proportional to the shear strength viewed in the particle rest frame. What does that mean is, imagine we have a profile in which the sigma x is negative to sigma yy. We should see some imbalance in the spin alignment, the density of the spin alignment. So to me, this is a very initial thing you would expect, because for the cases of spin polarization, the pseudo vector vorticity induced the spin polarization. Now, if we come to the spin alignment, the tensor components in the spin space, so we clearly expect that the shear tensor will induce the tensor part of the polarizations. The one interesting difference here is this shear polarizability is the primary reverse of odd, meaning it is sensitive to the dissipative effects. It should be sensitive to how the vector meson is interacting with the medians, how this vector meson is relaxed to the equilibrium states. So just like the shear viscosity could tell us much of the dynamical information of the medians, so we should look forward to the new information that this new transport coefficient, the shear polarizability would brings about. So here comes to demonstrate this physics even further. So we do the one loop computation. We consider the correlators between the Wiggler function associated with Wiggler function with the stress energy tensor of the Procol field. So we should use the dressed propagators. So the median effect is encoded in the self-energy term pi pairs. And by plugging this immediate propagators, we found that essentially this shear polarizability is a functional of the immediate spectral density of the vector mesons. So once you know the vector meson spectral densities, in principle, you can determine these transport coefficients at this one loop levels. So to further simplify the interpretations, we perform the integration and make certain by assuming the width is narrow as compared with its mass. And so this is the result. It's simply proportional to the real part of the self-energy divided by the decay width, multiplied by some kinematic factors. So physically, what does that mean is it tells us that how the shear could polarize the tensor polarization is proportional to the moment exchange squared divided by the decay rates. So this is a reminiscent of the Q hat for the jet median interactions, which is also scales with the momentum transfer scale, the transfer squared divided by the collision rate. So in this sense, I think it's well motivated that we introduce this shear polarizability as a new important transport coefficient which characterize the meson and median interactions. Two remarks still here. The first is in contrast to the usual Q hat, the psi is indefinite. So the psi could depend on which meson you are talking about because it's proportional to the mass shift. The mass shift can be either positive or negative. Another thing is several model studies of the self-energies tell us that this self-energy can be very sensitive to the mu b. So you expect to see the non-trivial beam energy dependence if you study the vector meson alignment, and the reason is very simple. The mu b determines the phase, essentially determines the phase space in which the vector mesons could interact with the baryons. So now the question is it possible that we can observe these phenomena? To see that, clearly we need the shears. And it seems to me that the shear is the cheapest thing that you could create the heavy collisions. Recall that the Billigen expansion, even for the Billigen expansion, shear is not zeros. The sizable shear already help us to understand the shear viscosities. And I think the chance to extract such coefficient is very good. In assuming that the magnitude of shear is order 10 of MUE, and that the ratio between the mass shift and the width is more than 10%. So this is the I think example to demonstrate. And so this is the explicit example to demonstrate what I want to see here. So let us just look at the J size. So this is from the study of the complex medium potentials. What this demonstrated that the typical widths, decay widths of the J size out of 100 MeV, and so is the mass shift. So this means that this coefficient using our estimations, this tensor, this shear polarizability parameters can be as large as order 1 number divided by the temperatures. This also means that you would expect the sizable signatures maybe up to 0.1 from such shear effects. And so I would encourage you to take a more careful look at this recent JPSI results from the Alice measurement. I wish to emphasize that in contrast to the widths, which can be constructed through other means, through the IA we choose, this mass shape is poorly constrained from the spin average observables. I hope this would convince you as an example that spin alignment indeed will serve as a new probe to the immediate properties that you could not even measure otherwise. So this brings me to the summaries. So I think just using the standard local equilibrium physics, some of field theory calculations, we could even demystify, if not fully solve, the various spin puzzles. And of course, if the system is out of equilibrium, you should extend these approaches once again in the systematic way using the beautiful Schwingertail ditch formalism. I do not get the chance to cover the story about the polarization of the fermions, but I do prepare a couple of slides for the discussion. So I will skip it and quickly jump to the summary about the Weickgenannt spin alignment. So we consider the limiting cases that the Weickgenannt is in local equilibrium, and in stark contrast to the common expectations, we find for several quantitative new expectations. First of all, is the contribution begins at the zeroth order at ingredient coming from the non-degeneracy between the longitudinal and the transverse transition dispersion and the modes. And at the first order ingredient, we see that the shear strengths will induce the shear polarizabilities with the coefficients, which depends on the medium directions. So as a result, we expect that the size and the magnitude of the spin alignment are very sensitive to medium directions. So this brings about the new opportunities that we may hope constraining the medium properties of Weickgenannt, which in turn will bring about the new license on the QCD phase diagrams if we do the quantitative modeling in futures. So I think there's a new directions that one should pursue. So this is the I want to say about my talk. And with Lori, we also prepared a few discussion questions. One is about the shear-induced tensor polarization that we just mentioned. I believe just by symmetry argument, this thing is allowed and should be there. So, and you can check it through the explicit loop calculations. But the question is there any simple physical interpretations? Can you actually, can anyone, I hope the audience could help us to bring about the new physical interpretations into these interesting phenomena. Another thing is in our explicit calculation, we found that this coefficient is proportional to the energy transfer, the typical energy transfer rate squared divided by the decay rates. And if I look at what Laura was presenting at the face value, it suggests it's proportional to the shear viscosities. So I think this is at least one qualitative difference. So the question is whether shear polarizability is proportional to the inverse of the decay rates, or maybe it's even connected to the shear viscosity. I think that's interesting. Another thing is I didn't cover the shear-induced polarization for the fermions. There's various theoretical questions, say whether it depends on some additional frame vector if you're using the different approaches. Does it depends on the pseudo gauge transformations? In my view, the most interesting question for this case is the result one loop exact or not, whether this phenomenon is dissipative or not. And more, in my view, even those qualitative questions have not been fully addressed. So with that, I would like to end today's my presentation.
So thank you very much, Yin, for this nice talk, and you also introduced the discussion. But first, let me ask if there are some urgent questions, at most two, as I said, for this talk specifically, and then we move to the discussion of both talks. Okay, so I see, I'm sorry, I saw three. Okay, there are two raised hands. Xinli Sheng first, please.
Okay, thank you. A very nice talk. Hi. I have a question about the cell-induced polarization. I think this part is not sensitive to the type of meson. So if the spin alignment for the meson is dominated by the cell part, then how to understand the difference between phi meson 000 and the chaos 000?
So my quick answer is, maybe I didn't explain clearly, so this thing is proportional to the size of the mass shift, and this size of the mass shift can be different between the different vector mesons, and currently it's not fully constrained theoretically. So the size, so in short, the size can be different. Delta m can be, the value of delta m, say for phi, can be different from delta m for chaos. Maybe they are more expert, which could correct me if wrong, but my understanding is currently there's no first principle constraint on the size of delta m for the different species of the mesons.
Okay, thank you. Another question, maybe a comment about.
Let give Ai Hong Tang the chance to ask a question, and then we postpone the further questions to the discussion session. So Ai Hong Tang, please.
Yeah, Yin, very nice talk. Yeah. Could you go back to this cartoon where you show the longitudinal and the transverse mode?
So the cartoon, yeah.
Yes, this one.
This one. Okay.
So yeah, I already told you in private, but I'm just pointing out to the audience. This imbalance between the transverse and the longitudinal mode is just like the local spin alignment in meson's helicity frame. And indeed, this is the one thing we check. So we want to see how much local spin alignment in helicity frame will result in a change in the global spin alignment. So we take two values, 0.2 and 0.6. Those are already two extreme values, crazy numbers. And then when pumping into our simulation, we do that for phi meson and the K-star meson. We put in the spectra, V2, etc. Then we found out that for phi, this local spin alignment will result in a change in the global spin alignment by the on the level of 0.1%. For K-star is on the order of 1%. Because now K-star measurement is, the error is large, but for phi, it obviously is not enough to explain the large global spin alignment we see in the data. Just to point out.
Yeah, sure, but yeah, I think still this depends on how large this splitting is. So for example, if this is the very high density results and using the summer rule, not the first principle, but I think if splitting as large as 50 MeV, I don't think you would get
that's remind me another point I want to make. Sorry. Yeah, so if there's one mode dominant, say transverse dominant over longitudinal mode or vice versa, then you would see a large splitting of the measured phi mass between the measured phi mass and the PDG value, right? So I just go back to check the analysis. In our analysis, the measured phi value, the difference between measured phi value and the PDG value is at most, I think 2 MeV on that level. So it's not possible to me.
Yeah, that would also be interesting if we could constrain the mass splitting at least we can put the upper bound. So that's
right. There's no dedicated analysis on this, but I just went back to see some old analysis. I see our method of phi value is only differ from the PDG value by a couple MeV at most, if there is a real difference.
But yeah, maybe, but still I'm not sure it's around the TC. How could the mass shift be such small?
Could you say again?
So imagine we are heating up the system near the TC. I couldn't imagine the mass shift is only a few MeV. Maybe I'm wrong, but
yeah, for phi, I will check for phi. That's the value we got is very close to PDG value for phi. I'm talking about. I only checked for phi.
Sure. Yeah.
Okay. So I also believe that I mean, if I understand in this method of Yin, that so he has a formula for the polarizability. I don't know if this implies that the observed mass shift of the phi peak should be, say, related to this polarizability. I don't know. This is something to be.
Yeah.
I don't know if it is say a straightforward implication.
I think the quantitative computation needs to be done to determine the prefactors. After that, we can talk about it.
Okay, so I believe let's thank Yin again for this very nice talk. And now the discussion session begins. There have been lots of interesting statements in these two talks, and really intriguing. So I would have liked to ask very many questions over the last hour. So I believe that this this is one of the first time that I've seen the first time maybe I have seen something based on heavily based on quantum field theory at final temperature for the alignment. So this is very interesting. Also, I was really very interested by the fact the pseudo gauge dependence mentioned by Nora. So there is a lot of interesting stuff here. And so I think that we can start discussion session by, so you can raise your hand, and I see already two raised hands. So the first was Enrico Speranza. So please.
Hi. Okay. So I would like to have to ask a question about his talk, actually, following up a little bit on what was discussed before. So, so a few years ago, actually, we also showed that even virtual photons in global equilibrium, so without rotations, so at order 0 in gradients, so they have some finite tensor polarization. And this, I think, is consistent to what you find, actually, that even at 0th order, you might have some effect. The problem is that we also calculated, we had a very simple model with just, production, thermal production. The problem is that when we calculated with phi mesons, the effect was very, very small, much smaller. So for the virtual photon was on the order of 10 to the minus 2, something like this. So anyways, for the question instead, so how do you expect that your result will explain the the centrality and the center of mass energy dependence? Because if it is if the major contribution would be like the shear term, how do you see that would reproduce the fact that a lower energy is higher, or that higher centrality is higher and stuff like that?
So I think my quick answer is you need to do the quantitative studies. So the reason I'm showing here is just for the first mechanism you already see just by kinematics, you will get the side flips from the lower PT to the large PT. So that's why I think this is worth checking. But turning to the shear-induced contributions, you can already see it's simply essentially proportional to the ratio between the real part of self-energy divided by the decay width. So I think the And the mu b dependence is quite expected because, as mentioned, if you increase mu b's, there's more ways that the Weickgenannt mesons can be interact with the baryons. And once again, I would encourage our hydro friends to do the calculations, but clearly the shear contribution is also sensitive to the centrality. So with that, I think I'm not saying this is a solution, but I believe the data does not look very mysterious to me at this level.
So you expect that also the dependence on alpha, this ACE-H, will play a significant role, right? Not only the sigma.
Sigma, we are roughly speaking, determines the centrality dependence.
Yeah.
The shear depends on the centrality, but clearly the self-energy should non-trivially depends on the baryon densities.
Okay. Okay, thank you.
Ulrich?
Yeah, this is a question to Nora. If you could show your last slide again.
Yes, but I can only share. I think if the sharing is stopped.
Shall I stop sharing?
Yes. Which slide?
The last one. Yeah, this one, yeah. So I'm trying to get the systematics right of or understand what you were saying. In particular, the distinction between what you find for spin 1/2 and spin 1 particles. So I understand there is no tensor polarization for spin 1/2, but there is one for spin 1 and any spin higher than that. Is that correct?
Yes.
Okay. So spin 1 just has vector polarization, but spin 1/2 just has vector polarization, but so does spin 1 also has vector polarization. How
Yes.
do the vector polarizations between that you calculate in the spin 1/2 case and that you calculate in the spin 1 case differ from each other?
Not much. I think so. We did not calculate yet the polarization for spin 1 because it doesn't really play a big role in experiments, but it should be similar.
Why do you say it doesn't play a big role in experiments?
Because it just what the measure is a tensor polarization. So in this.
Okay, so they haven't provided data for that yet, but I think
yeah, so this
would be interesting to predict that.
yes, also.
I would have thought that basically the vector polarization should be structurally the same, with the only difference being related to the Casimir of the spin group. I mean, basically the magnitude of the spin in some way, but you don't have that information.
Also, what you can say is that the spin moments they look similar, and the equation of motion they will also look similar, but of course they will also have contributions from tensor polarization which are not here. But we don't have the full equations of motion yet.
Yeah. What I found interesting is your statement that the tensor polarization not being constrained in any way by conservation laws relaxes faster than the vector polarization. What is the, I mean, what conserved quantities do is when you are initialize them out of local equilibrium, then they first move towards the local Navier-Stokes limit before they approach global equilibrium at a much longer scale, and that time scale is much longer because of conservation laws. But the relaxation time from an arbitrary off-equilibrium initial condition to the Navier-Stokes limit is not really constrained by conservation laws, or am I misunderstanding that?
I'm not sure. This is probably something one needs to check more carefully. So the relaxation times for this, when treating them dynamically and how large they are, this is probably something that one would need to check. But I think, I mean, in usual hydrodynamics, if one treats the components of the momentum tensor as dynamical, and the other ones are getting approximate, and it works well. So
Yeah, I understand that, but I don't quite understand the rationale that you gave for splitting them the way you did, because I didn't. Maybe I missed something. If you can say again, what is it that makes the relaxation of the tensor polarization to the Navier-Stokes value faster, so that you can just use that and you don't have to look for its dynamic evolution, than the approach to Navier-Stokes in the spin polarization case, in the vector polarization case?
yeah, so in the moment it's just a first study. So what we will do later is we will treat them dynamically and we will see how fast they relax. So what we do now is like doing Ford moment approximation and treat only the components of the energy momentum tensors dynamically. Everything which does not appear in any conservation equation, we just approximate by the other moments by Navier-Stokes limit in this case.
Okay, thank you. I understand what you're doing. I don't quite understand why you're doing it, but we can discuss that offline.
Yes, that's okay.
Okay, so we have more questions. Oh wow! So the next one is Xinyang.
Yes, this is just a couple of comments. The first one is there's a pattern between different flavors like phi meson and k meson spin alignment. No matter what kind of dynamics you're considering, whether it's due to spin polarization plus combination or versus shear induced polarization, I think one really have to answer this question. And I don't believe the difference is if the difference is caused by the intrinsic interaction or the structure of the meson in medium, and the difference cannot be like 1 order or 2 orders magnitudes difference. Of course, the current experimental data on that is still not precise. So in this case, I think as we move along, it's very critical to reduce the the uncertainty and then see the difference, the quantitative difference between the phi meson and the K star meson spin alignment. And secondly, if at least according to, no matter whether it's recombination or shear induced polarization, and if that's the case, you can actually reconstruct the same phenomenon like spin alignment by looking at lambda spin correlation, because that you can also construct the tensor. And of course, lambda is 2 mesons, so the correlation probably is different than the single meson, like phi meson. But that measurement, if this can be done, I think it should be done, can also address that kind of problem. Okay, thank you. This is just my comment. Maybe the experimental colleagues can comment whether it is feasible for them to look at lambda, for example, spin correlation.
Yeah, this is, I think, an interesting point. I would like to add one more question to the experimental colleagues, because I don't remember that. Was the phi meson alignment measured both at RIC and LHC? And is it the sign in agreement between these two measurements? The sign of rho 0, 0 minus 1/3? I mean, does anyone know about it?
What do you mean sign agreement? If we
I mean, the question is whether rho 0, 0 minus 1/3 for the phi meson has the same sign at RIC and LHC energy.
The error for the at least result is large, right? If we, I think if we integrate over the similar kinematic range, they're about to have the same sign. And let me just give me 1 second. I think they have the same sign. Yes, for phi, they have the same sign. If we integrate over similar kinematic range. We
So
cannot hear
there are
you.
more. Sorry, there are more questions to come. So I would like can ask people who ask the question to lower their hand. So just not to. Oh, there are 4 of them. I don't know the priority. So let's start. Arpandas.
Yeah, so I have a question to Nora. So you introduced this quantity spin chemical potential and the difference between the spin chemical potential and thermal vorticity at some dissipative correction. So what is the exact form of this dissipative correction, and does this dissipative correction also depend upon different pseudo-gas choices?
So the sorry, so the difference here is this one. So this is actually determined by the equation of motion. So from the conservation of the total angular momentum, okay, the rest of the equation of motion, and this determines the spin potential, or the difference between the spin potential and thermal vorticity. And this, I think, does not depend on pseudo-gauge, because the conservation equation for the chill lambda mu does not depend on pseudo-gauge.
Okay, thank you.
Okay, so next question by David Wagner.
Yes, I have more of a response to Uli. So actually, we do have some results for the vector polarization of the spin 1 particles, and actually, so you get a factor of 2, as you said, because the spin magnitude is twice as large. But as Shuai Liu also said in the chat, if you look at the polarization, there will also be you will also get a factor of 1/3 due to the degeneracy of the spin states. So in total, I think the factor 4/3 that was listed in the chat is we also get at least in equilibrium.
In equilibrium, yes, okay.
Yes, in equilibrium. So for the dissipative case, as Nora correctly said, we have to write down we have to find the equations of motion for the moments, but they should actually be quite similar to the spin 1/2 case.
Thank you.
Xinli Sheng.
Yeah, I have a question to Professor Yin Yi. So can you share your sliders?
Yeah. Sure. Yeah. I will. Can you see that?
Wait a minute. No, not yet.
I mean, not yet. Let
No,
me
I
try
cannot.
again. Sorry for that. Share the screen. Yeah, sorry for that. Very. Maybe can you directly ask the question while I'm trying to load the slides?
Okay. Please go to page 17. In this page, you write that sigma YY contributed to the spin alignment. So my question is why sigma XX and sigma ZZ does not contribute?
Yeah, sorry, I still have trouble with the screen sharing, but I can answer directly. So I just demonstrate if you consider ring Y as the quantization axis, then you will see the contribution from sigma YY viewed in the particle rest frame. But if you choose a different quantization axis, so then you will get the contribution related to sigma XX. So in other words, I would also encourage our experiment friends to try to measure the delta rho 00 from different quantization axes, and so that I think this can be used to distinguish different mechanisms.
Actually, they are related. I mean, the contribution, if a contribution to rho y is positive, then its contribution to rho x is negative. So sigma XX, if its contribution to rho x is positive, then it must have a negative contribution to rho y. So I don't know why you don't have this term. So okay, thank you.
Sorry, there's a term. I think eventually the trace is 0. So I think just for illustration, sorry, I didn't write down explicitly.
Okay, thank you.
Francesco, may I just ask a question just to Xinlian? Maybe that's one thing. I mean, a short question, but I'm not sure I fully understand his comment.
Yeah, please go ahead.
So my question is just the parametric power counting. The recombination model predicts the correction is gradient square coming from the recombination of polarized quark by the vorticity, and the shear tensor, the contribution is simply proportional to shear tensor in the near equilibrium limit. So parametrically, is the first order ingredient. So from the parametric power counting, I think the later effect potentially can be order of magnitude larger. So that's so I don't understand why.
Not. I mean, of course, if you only consider vorticity induced, indeed that's the case. But if you introduce external like a field, strong field coupling to the quark, that's okay. If you introduce, for example, in terms of like meson quarkling model, there is some kind of external, field, and this is in Qinhuang and our paper we already have done that. And then the polarization tensor rho is essentially proportional to the local fluctuation of the field, instead of the linear one. Linear one, of course, I mean, that contribution, this external field contribution to lambda polarization is 0, because that is linear, and then the average of the field is 0.
But maybe, sorry, maybe I want to take the opportunity also ask a question. I'm a long puzzle this, but what pickups the preferred direction? I understand, imagine we have the field fluctuation in one direction, the other direction. But the question is, what makes delta rho 0 tells you that one direction is more preferred than the other direction. So what is the mechanism which pick up this preferred direction?
Well, the answer is because the anisotropy in the medium.
You mean like it should scale with V2 or V2 square or something like that?
Well, not really, but the elliptic, the momentum spectrum, the anisotropy really play a role there.
So I think we should probably go on with the questions. There is one more question by Shuai Liu. Yes, please.
Okay, basically, I just have a question for Xinyan, probably, or say probably also for Dr. Ko, for the people who know these hadronic interactions, experts on these hadronic interactions. Basically, I think the key point is that over psi, the psi of the tensor polarization, or say the psi of the rho 0, it's kind of depending on the mass, immediate mass shift. This immediate mass shift is kind of, yeah, from my own experience, it's just due to how to set at the scattering is more like attractive or repulsive. So that will cause this mass shift to be positive or negative. In my previous calculation in quark level, I see this can be either way. So if the 2-2 interaction, 2-2 interaction on average is more attractive, then it can be a negative mass shift. Or if you do have this repulsive interaction, it kind of can shift the mass up. So I was wondering whether or not this chi meson, or say how this chi meson and phi meson, do they have the same hadronic interaction, or they have kind of different hadronic interaction? They can lead to a slightly different immediate property, so that can make the sign different. So basically, I just ask whether or not this is possible. So for Xinyan, probably.
Yeah. Okay. Maybe I can answer this question.
Yeah. Okay, thanks.
Yeah.
Okay.
Because the difference between the phi meson and the k star 0.
Yeah.
Yeah, that's one difference, and we have stated in 2 of our paper already. So the difference, the fermion, you know, the fermion, the lifetime of the fermion is longer. So it's it will decay outside the fiber, while the K star 0 is very short. So the K star 0 suffer more medium influence by the rescattering, like more, I think, stronger interaction with medium for the K star 0 than the fermion. So this makes the fermion very special. So
what is the decay rate?
I don't think there's any difference medium correction to the mass of the fermion, because they never saw this the correction to the fermion mass in experiments, in any experiment.
That's inconvenient because the experiments always measure the vacuum one. The only thing you can measure this, the only thing you can measure this in median spectrum function.
But it doesn't matter. But it doesn't matter.
Is for the rho. So the other things is
exactly. The rho has a very short time.
Yeah, but however,
they decay inside the fiber like the K star 0, but not the fermion.
Yeah, but the fermion, for example, the picture is not like that. The picture is that it's kind of, you start, at the kinetic result, you carry this in medium properties, then you freeze out outside. It's still like
the outside the fiber.
Yeah, outside, but however, at that part, you spin freeze out at the boundary of the phase.
Of course.
That's the point. Otherwise, I understand there is no in vacuum, you cannot observe the mass.
This is only one difference. This is only one. Another very, I think, very big difference between fermion and the K star 0 is that the fermion is a quarkonium. So the field felt by the S quark is just like as the field acting on the S bar quark. So it's very special. But for K star 0, it's not Freeman neutral, you know. So it's the field acting on the S quark is different, very different from the D bar quark. So there's no correlation. So when you see, I mean, there's also I can answer the Yin Yi's question. Why the square term survive? Because the square term is a square, real square. It's even the field fluctuates strongly. It has a non-vanishing value. I mean, if you look at the linear term in field or in vorticity or in shares, whatever, the linear term will suffer severely from the fluctuation. I think that will suppress the value, the net value of the linear term. So,
Jing, if I follow your argument, do you have prediction for Jeb psi?
Jeb psi, the Jeb psi I don't have yet, but we can predict fermion.
Why only 5? You argue quarkonium, Jeb psi is
quarkonium. We are studying quarkonium such as Jeb psi, but not yet, but not finished yet. We are looking at the Jeb psi problem, but not yet finished.
Can I ask
I think the quarkonium also get the positive deviation from the 1/3. You know, the same. The quarkonium is like a fermion, but it's very different from the K star 0. Okay, thank you.
Thank you.
Can I maybe just ask a short conceptual question, if I may?
Sorry, let me ask you for say if there are some questions on different topics, or so there have been many topics that they mentioned in these 2 talks. So if anyone has a special question. Sure.
Yeah, I have a question for Nora, I think. So
yeah.
Yes.
Please.
Yeah. You mentioned that so the spin 1 degrees of freedom is very different from the spin 1/2. So is it correct? So it's not the fundamental degrees of freedom or something like that?
Well, yes, the spin 1 have more degrees of freedom because they have the the tensor polarization.
Oh yeah, here. You say the spin 1 particle feature additional degree of freedom. What's this? What does it mean?
Well, they have tensor polarization. So I mean, for spin 1/2, you have only 2 spin directions, and for spin 1, you have 3 spin states, and you have tensor
I see.
polarization, which is
You say
small.
that it has more degrees of freedom. I mean,
Yes, right.
Okay. So, yeah. Okay, thank you.
Okay. I would like to ask a question to Nora myself. So I think this is one of the most interesting points that have been raised over your talk, which is the pseudo gauge dependence. So, and I would like you, if you can further comment on it, especially whether the set of dissipative coefficients that you have found are dependent on the pseudo gauge. I think that this should be emphasized because if there is a dependence on pseudo gauge, this means that it is the dependence of the fundamental, say, quantum field theory. So on the choice of the stress energy tensor operator. So, so my question specifically is, if in your study you found that the coefficients depend on the pseudo gauge, as I expect, or even the very set of terms depend. So if there are some terms which appear in a particular pseudo gauge, so with a special choice of the spin tensor, or say some terms disappear.
Yes, right. So indeed.
I mean, I'm talking about the dissipative terms. Yeah.
Yes. So if you have the full, so you have this infinitely many taus, right? And if you were able to take the full theory, so to treat all these taus as dynamical and derive a motion for them and solve them, this would be independent of the pseudo gauge. This isn't, it's just what it is. But of course, it's not possible. So we have to truncate. So we have to select which taus we treat dynamically and which ones we do not treat dynamically, but approximate them somehow by the others. And this choice does depend on the pseudo gauge, because what we do is that we treat the ones which are part of the spin tensor, which are these ones, we treat dynamically, and the others we approximate by those which do appear here. So if you had a different form of the spin tensor, this would be a different set of modes. So if you had chosen the Bell and Panther, there would not be any dynamical modes because there's no spin tensor. If you had chosen canonical,
is this an effect of truncation or?
Yes, it's because of truncation. So let's say if you have the canonical, you have actually only these 4. So the canonical only has actually 4 degrees of freedom. So you would have only 4 dynamical moments.
So to summarize that, you think that there is no dependence on pseudo gauge eventually, as far as the observable Pavlobansky vector is concerned. Is it your say statement?
So in principle, in the exact theory, there's no pseudo gauge dependence. So if you look at this expression, I think which you also have this expression does not depend on the pseudo gauge. But at some point, we make some approximation for this f, so we decide which moments we take into account in this f and which not. And this choice depends on the pseudo gauge.
Okay. You know that, but the distribution function depends on a density operator, which in turn may depend on the pseudo gauge. So I think this is still to be settled. Okay, so thank you. Are there more questions? I think that we are 10 minutes beyond the time. So if not, I think Xiaofeng, I think you may close the session.
Yes. Thank you for everybody to joining this nice two seminars. And I think they will have present a wonderful result. And also, thank you for Francisco to chair the seminar. Thank you very much.
Yes, thank you so much. Thank
Yeah,
you.
it was a
Laura.
pleasure.
Thank you.
Yeah.
Bye.
There have been lots of interesting topics and discussion. I think this is, I think, was very good idea to have this joint seminar. Yeah.
So I saw Chongming Court have something in the chat window. Are you going to say something?
So there is one
I
extra
was
question.
talking to, sorry, I was talking to Saidu. I mistyped it to everyone.
Sorry. Okay.